Right. All right. Good evening. So last class, or last session, I guess, we looked at machine learning, a little bit neural networks, and then we looked at how it can be applied to robotics and autonomous systems. So I had so many videos that I played, and the last set of slides, like 2 or 3 slides, I was talking about deep learning and where is it going actually. So, so if you look at it, I can show that's, let me show you the screenshot share on that. And then, we did talk about that a little bit, but I didn't talk about from the perspective of the amount of data. So let me show you, let me share the screen. Maybe you can see this. So this was the thing that I was showing. There's a lot of interest now about using games, how you can get the feedback, how you can actually make the system more intelligent, right? So like an agent, and it basically takes an action, applies to the environment. And in this case, it could be a game like a Breakout or Space Invaders. And what are the actions moving this bar left or right or top or bottom? And the goal was to maximize the score. So why are we looking at this right now? Because remember, I mentioned that you have to process lots of data. So here, if you look at the current state, is an 84 by 84 pixel, and you take 4 frames. So constantly, the longer you play, the more frames you're going to process. There will be lots and lots of data, and that's being processed by this network. So you have this network is a convolutional network. You have about 16 8 by 8 convolutional strides. Then you have 32 of them, then fully connected. And the goal output was mainly the number of actions. So, and then I played a lot of videos essentially to show you how the system learns without programming. I think that's very important. We are trying to avoid that. So this generates tons and tons of data. And some of these games are trained at 4 million iterations. Okay, so basically there is an offline training, and then you try to use it in real time. Okay, so there's a tremendous amount of data. That's what basically I was trying to talk to you. And today what we're going to talk about is primarily we want to see how we can look at this problem from the perspective of big data, and what are the challenges of big data. If I can get my slides here in a second. So that's what we are going to do. And then we will see if we can look at the challenges, maybe the perspective of solution and so forth, okay? So learning with big data, challenges, perspective and solutions. And I gave you one example where as a human, you process tons and tons of data from the eyes, from the ears, sense, touch, so forth, okay? So again, if you have questions, you can shoot me an email. You don't, we will have a few minutes at the end. So you can ask me questions. Otherwise, you can shoot me an email and then I can respond to your questions. So what are the objectives, okay? So the objective is you have data that's coming in, like pixels, for instance, in the example. And the goal was to make decisions, or we can say actionable insights. So the fundamental question here is what generates data and how much? I think that's the important question. So we call that as smart environments, okay? So like, we have smart homes, smart, smart car, and so forth. So fleets of vehicles, machining centers, process control, smart grid, and smart healthcare. All of them going to generate large quantities of data. So the question is, how large is this? Okay. So there are other examples. Okay. For instance, a jumbo jet generates about 650 terabytes of data over one Atlantic crossing. So there's a tremendous amount of data that you're going to generate when you have so many sensors. A human activity, in fact, generates about 1 gigabyte. Okay, so if you accumulate it over time, you're going to you will see quite a few amount of data. So one sensor, for instance, generates about very conservative estimate of about 2 megabytes of data a day. So if you add up all this, it's going to be tremendous amount of data. Okay, so we call that as a big data, and the last decade, this term big data coined, and there's tremendous amount of opportunity. So why is big data analytics important? Basically, what is analytics here? We are calling analytics is basically you take the data, you process that, and then you come up with a decision or an actionable insight. So that's basically, this insight is information. The data is in raw, in bits. So that information is most valuable for us. And that's what we are interested, what we call data analytics. Okay. So all these companies that are involved in Silicon Valley, Wall Street, they say that the most valuable commodity is information. So nobody cares about data, but they care about basically the information. So Google says that there were 5 exabytes of information created between the dawn of civilization through 2003, but that much information is now created in every 2 days. So that's an issue right now. Tremendous amount of data we are creating every 2 days because we use a lot of IoT devices. Each device has lots of data, lots of sensors. And so they are going to be quite a bit of data. So big data will spell the death of customer segmentation, force the marketer to understand each customer as an individual within 18 months of risk being left in the dust. So you can see that all these software companies are kind of very much interested how to convert the data into information, where Microsoft defines big data as a term used to describe the process of applying serious computing power to massive and highly complex sets of information. So here are some companies that have invested in big data and analytics. So there is a lot of growth in this area. There are a lot of opportunities for younger people. There's also a lot of interest and job opportunities and so forth. Okay, this is a growth area, as I mentioned to you. So what are some challenges with this big data? So why do we care about this? Okay, so you can see that some of these things are like heterogeneity. The data is not the same. There is also noise in the data. There's also noisy dimensions. We're going to talk about that a little bit. So I'm going to focus in these 3 because we only have about 15 minutes and the last 10 minutes are for questions. So the goal was to come up with some sort of analysis. There are other challenges which we call incidental endogeneity. And of course, you all know that when you have tremendous amount of data, there's also a computational aspect involved in it. So we're going to focus on today on these 3. One is heterogeneity, other one is noisy data, other one is noisy dimensions. Okay. So what is heterogeneity? So heterogeneity refers to the scenario where 2 data samples from the big data exhibits unique characteristics that are not shared among these samples. So that's the problem with big data. So if you take sample from 2 different places, the statistical properties are completely different. Okay. So if you look at it here is the big data sample space, for instance. And if I take a sample from here, the another one, there's a little overlap here. So we call this data as data available for learning source distribution, especially for training. And here is the purple here is the data observed during the real practice or real world scenario, which we call the target distribution. So there is not much of an overlap between the data we use it for training, if you are using it in neural network, or for testing. So because of that, the performance deteriorates. So a good example is the case where a neural network learns to recognize regular light bulbs in the learning phase, but is tasked to recognize CFL bulbs in the test phase. So here is a regular bulb, here is a CFL. So both these are bulbs, but they do not look similar. So what happens is they're all white, so there is some similarity, whereas they're not really the same type of bulbs. So certainly when you test it, then the neural network would have a problem recognizing the CFL bulb as one of the regular bulbs. So this is what we call a heterogeneity problem. The gap or difference between the source and target distribution is known as heterogeneity. So noise. So this is the other one that we encounter typically with all problems. Noise refers to those entities in big data that may distort the true characteristics of the underlying data distribution. So basically here, you are using data available for learning, which we have the source distribution, data observed during real practice or target distribution. And this data is because of the noise. Okay, and here is the big data sample space. So the image on the right, if you look at it, this is same as Lena and the same thing as here. So what the difference between this picture and the other one is this picture is more noisier version of this image, which we call Lena. So the image on the right is image that is observed during the testing phase. So typically what happens is many of us use this image to learn. So it learns nicely. But then when we try to test the image like this with a lot of noise, the classifier, it doesn't really work well in the presence of such noise. So that's the problem. We call that noisy. The other thing that we're going to encounter with big data, what we call is noisy dimensions. So it's like we're going to define, we have number of data points and number of dimensions, okay? Number of dimensions include number of sensors, which are going to describe the same image or same object. So noisy dimensions refer to the scenario where many weak features exist that do not contribute to the reduction of error. So if you look at it, scatter plots here, and you can see there is a lot of overlap. Okay, so scatter plots are projections of 100 observations from each class onto the first two principal components of the feature space. A projected data with the filled circle indicates here that indicates the first class, and the filled triangle indicates the second class. But eventually they actually overlap. The number of dimensions M in the data reduces the separability between the two classes. So as you increase the number of dimensions, so here M equal to 2, you can see nicely it's separated. But you think that as we increase the number of dimensions, like in the big data, you will be able to actually separate these two. But as you increase it, M equal to 1000, you see how closely these are, and it's very difficult to separate those red circles with blue triangles. So in other words, because the other dimensions will become like a noise, which makes it harder to separate them out. And so a lot of times, because of big data, this which has the higher dimensions, it's very difficult to basically classify these the data points. Okay. So this is one of the issues with big data. Any difference between the source and the target distribution, we call that as a domain shift. Okay, these are the technical or terminologies we use. Okay, so what is the analysis problem, and why is this big deal right now? Okay, so you saw that I took just 3 aspects in there, and so one is the characteristics are not different if you sample them at 2 different times, and the second is that it has noise in them. So basically, when you test it, that data points are completely different. You have a problem. And the third one, we talked about noisy dimensions. So typical analysis with this problem, where is my cursor? See my cursor here. So the analysis problem, back to share. Not sure here if I can see the. Okay, so something happened here. 1 second, let me go back there. Okay, so the issue with this is that so the issue with this analysis problem is that you have to look at a reduction in dimensions, then you look at some nonlinear relationships between data and you extract some features, and then you predict or classify, which has some issues in here. The incidental endogeneity plays a bigger role. Heterogeneity also plays a bigger role here. And you see the noisy dimensions play a role in the feature extraction. And eventually you try to predict, okay? So what are the different ways to extract? So we use what we call distance measures, wavelet transforms, Fourier transforms, dimension reduction, feature selection, learning-based extraction. Then you come up with a mapping, which basically is Y, which is a prediction, some nonlinear function of the feature space, which is G of X of X. And different prediction based on applications. Use it for fault diagnostics, classification, regression, clustering, and so on, okay? So there are two major ways to do this in big data analytics. One is dimension reduction based approaches where you reduce the dimensions. The other one is basically learning based approaches. So I'm going to focus on learning based approaches in the next 20-25 minutes, okay? So introduction to learning based analytics. So let's say you're trying to recognize these objects. Now look at that. In these objects, there are parrots, but not all of them are parrots. They look like parrots, for instance. So you can see here, these are not parrots. For instance, these are not parrots. They're avocados with some, strawberries. They look like parrots. And so the goal was to really identify which of these images are parrots and which of these images basically have avocados. So this is a very hard job for a computer, but it's a lot easier for human beings, okay? Humans can recognize thousands of objects, but in order to have a robot with a camera to recognize this, it's very difficult. And if you look at one of these data sets, ImageDat, let's say it has about 1,000 objects, about 644 gigabytes of data size. So for a computer or an embedded system, this is considered as a big data. But actually, you got to even go higher if you really want to go into the big data. But this is the bare minimum, but still you can call it as a big data. So how do we learn such things from this large quantities of data? The solution would be deep learning. And that's what people call about, people say, well, we can use this using deep learning. So now we're going to talk about what is deep learning. So deep learning refers to the case where in the neural network with large number of hidden layers is used to approximate a function. So I talked about the last session, function approximation. So deep neural networks are supposed to be a good function approximators. So we're going to use that here too. So, but then as you increase the number of layers, you're going to have tremendous number of weights, or we call parameters in the neural network. Lots of data required to learn these parameters. So that means that the more amount of data you're going to use, the more the size of the network is going to go up. As a result, you see that these connections are going to go up. The number of weights are going to go up, or the number of parameters are going to go up, okay? A traditional neural network has about 2 to 3 layers. A deep layer neural network would have more than 3 layers. So here is the thing. And so the input layers are data points. In the case of big data analytics, the output of these output layer represents the probability, okay? So this is how these networks are designed. And examples of deep learning architectures, for instance, include, for instance, Alex network, it is about 8 layers in 2012. VGG is about 19 layers. And GoogleNet is about 22 layers. So why are these number of layers keep going up? And what are the reasons for it? And as I said, the image that we're trying to classify this image. So if you look at it, it's basically increasing the number of layers results in reduction in prediction error. So in order to predict this is a parrot versus an avocado. So you can see in 2010, it has a shallow layer network. It's the classification is about close to about 30%. It's very high. But as you increase the number of layers, you see the shallow, then you're going up to 8 layers. And as you increase the number of layers, and you can see the classification error keeps dropping down. And as you go up to 19 layers, it is about 7.3% error. And as you increase it to 22 layers, which is the Google Net, it even further goes down to 6.7% error. Now look at that. In 2015, we used about 152 layers. Then you can even bring it down to their about 3 to 4% error. So this is the problem. As you increase the number of layers and it increases the size of the network, actually you can improve the error in prediction. So that's the reason why we talk about deep learning. So why is the deep learning works? The fundamental thing is biological plausibility. So we use it deep learning inside our eye cortex, visual cortex. It's proven, okay. And also they have shown by using this manifold entanglement perspective in 2017 that you can actually use very complex network generate very complex decision boundaries, which is very useful for prediction. But mathematically, we can also say that functions which can be represented in polynomial number of nodes with k layers may require an exponential number of nodes with k minus 1 layers. So that means that if I'm using one layer less, I really have to go with exponential number of neurons in each layer, basically. But nevertheless, deep networks are universal approximators, and they can approximate very highly nonlinear functions with deep networks. So basically, that's one of the things. So I'm not going to show some live demo pretty much because of the time. So I'm going to skip that. So what are the challenges? Okay, we talked about it. Although it was theorized in 1980s, it has become only recently, it's more popular because deep learning requires large amounts of label data. So that means they're used for target. And so most of the deep learning methods use what we call supervisory learning, okay? So a driverless car development requires millions of images and thousands of hours of video. So this is what I was talking about with Tesla or something. They have to really train it on a track. And if they change the background, they still have a lot of problems. So the question is that data is considered as a big data. Deep learning requires substantial computing power. So that means you're looking at GPUs. And more recently, I think there are parallel architecture machines and GPUs and they're becoming more and more popular. So we're going to address that. This is one of the reasons why it's popular now than in 1980s, okay? So we use deep learning on the big data and we try to solve those challenges such as heterogeneity, noise. And what we're going to show is that the performance degradation and poor generalization error will increase in data noise and heterogeneity, but with our method, we're going to minimize that. And one of the other problems we face with deep networks is vanishing gradient. So we're going to talk about that in a second. So mostly when you use large quantities of data, okay, we're going to get into a problem called generalization error. Okay, that's what we call as a domain shift. Okay, so the difference in the neural network output due to the domain shift, we call that as a generalization error. Okay, so the sample space is underrepresented in the learning space because it's so huge. You only can take small pieces of data and use it for training, whereas the target distribution is so huge. Sometimes there will be a large amount of error. Okay, so the solution is generate data to represent the gap and compensate for it through what we call neighborhood principle. So basically what it means is here is the let's say entire sample space. You're using these blue circles only available for data, and these white spaces are the ones that we call as neighborhood. And basically we don't have data in these and we are not going to use them for training, and they can create a lot of problems. And because of that, if there's a noise, that data point will come in the white space, and that's going to create a large amount of error. And so how do we fill this white space? So what we do is we basically perturb this, we call it as a distortion in the training data, and that's going to generate some noise and it's going to generate some data around this blue circle. And from there, we can use that data to train the network. And that additional data would help represent the actual big data space much better. And it's also used to minimize the generalization error. Okay. So in the analytical development, what the goal was, we formulate this problem as a optimization problem. So you basically define a quadratic function in terms of the generalization error. And then the goal was you try to reduce that error. So the error is defined as the actual output of the network and the target value. And then the goal was to minimize that. And that's what you're doing, y minus. You're basically looking at a small change in the neighborhood, x hat plus delta x, a little perturbation, and that basically is bounded. You don't want to take a large step. So you define a quadratic function C as E transpose E, because this one is always positive, and the generalization error E transpose G, EG, and the goal was to minimize this cost so that we can minimize the error. Okay, so that's the goal. So we want to minimize C by selecting the proper weights. Okay, and that's what we're calling as a training of the deep learning. Okay, so what is the traditional approach? The traditional approach we talked about last session, we call backpropagation or stochastic gradient descent. So if you have not attended my session last time, you're going to have trouble understanding what we are talking about. So please go through that. Those sessions are recorded. And I remember Dr. Karthik, he posted that video as a YouTube video. I looked at it. So make sure that you go through that and try to understand this. So traditional learning, we talked about backpropagation or stochastic gradient descent. So here we use this, see that same cost function. So what are we trying to come up with? The weights is basically proportional to the partial of the cost with respect to the weight. So this is what we call stochastic gradient descent, where alpha is the learning rate. So now when you're talking about more than one layer of weights, we're going to use a simple, what we call the chain rule, right? Our product rule. We have learned this in high school math, and we also learned this when you guys are in the first year. So we learned this, the partial D, partial C over partial WI. We want to go through like a chain rule or product rule, partial C over the activation function in the Lth layer, and partial activation function over the previous layer activation function, and so forth, until you come to the partial activation function over the partial weights. So this is what we call as the product rule. And then what the question is, what happens when the number of layers increase? As the number of layers increase, usually the activation function varies from -1 to +1. And as you increase the number of layers, we call that as a vanishing gradient. Basically, these values will become smaller than 1. And remember, when you multiply two quantities less than 1, 0.9 times 0.9, it becomes 0.81, which is less than 0.1. Okay, so what happens is, as you increase the number of layers, and if this gradient, usually the activation function is less than 1, basically what will happen is, as you make these products, the overall, the deep network output will become less and less. Eventually the values disappear. We call that as a vanishing gradient. Okay, so why is it important for vanishing gradient, or why do we care? So what will happen is, as the output, there's a large error, but then as you propagate backwards, what will happen is, because of the vanishing gradients, these the signals that are used to train the input layers are very small. So these weights are not going to get tuned compared to the weights which are in the output layer. So what will happen is, these weights will slowly become 0, and therefore the output of the network will simply vanishes. So the layers which are close to the output, they'll learn fast, whereas the layers which are at the input, they learn very slow. And these are some of the drawbacks of vanishing gradient. And get stuck, it's a problem. Okay, so you can see here, as the number 1, so it's a lot better, but as you increase the number of layers, you can see it quickly becomes, vanishing gradient problem. So one of the popular solutions for this, we call, is changing the activation function. So activation function f of x is x, if x is greater than 0, otherwise is 0. So what we do is, we call that as the ReLU activation function. You take the derivative. The derivative always stays between either 1 or 0. It will never be less than 0. Okay. So small, but then it mitigates the vanishing gradient. But what are the drawbacks? Small weight values can still lead to vanishing gradient. So when you look at the actual product rule, you see that you take the product with respect to some weights, then it becomes a gradient, but then you're multiplying by the weights. But even though you fix this problem of the gradient of the activation function, but what happens when these weights are very small, then you get multiplied by 1, and then this can still have the vanishing gradient. So how do we fix this problem? So the way you can fix this problem is that we can use what we call error-driven learning. Okay, so instead of propagating the error through the network, okay, like that's why the name back propagation or stochastic gradient, we basically use the error, the output error directly in each of these layers. Okay, so if you do that, and then you use a B matrix to enforce exploration. Okay, the exploration is the perturbation term. So by doing that, and then you add an extra term, which we inhibit training in noisy dimensions. Remember I talked about the noisy dimensions? So larger decay along noisy dimensions, smaller decay along non-noisy dimensions. So if you do that, then we can mitigate the vanishing gradient problem. We can inhibit noisy dimensions. We also can actually prevent noise affecting it. And by doing this, basically we call this method what we call error-driven learning. And we choose this BI, which we call exploration. We sample at random while ensuring non-singular values of this particular product. This becomes a matrix. So then you can find out the singular values and singular vectors. And we can use that to determine the direction, and then we can still use the gradient descent, okay? So this is one of the popular methods, and we can test it on a wide variety of big data sets, okay? So you can see that there is ASAN. I just used a few of them, Cypher 10, and you can see P and N. N stands for number of data points, which is basically the rows, and P stands for number of dimensions, which is the columns, okay? So in the ASAN database, you have 10,000 columns and about 7,000 data points. So only a few data points, but tremendous number of columns, okay? In Cypher 10, you have fewer number of dimensions. Look at the data points, about 60,000. And there are some rolling bearing data set. They're only about 11 dimensions or 11 sensors, but look at 400,000 data points. And so there are lots of data sets. You can keep talking about it, which has millions of data points and also thousands of dimensions. So this becomes the big data, and each of them have like different reasons, like object recognition, discrimination task, hand digit recognition, and so forth. There are so many different applications, and you have P and N, which is very, very critical, okay? So we want to evaluate how these methods do. So we consider the problem of classification, for instance, and let's say one example is fault diagnostics and classification, okay? So the number of dimensions in the data range that we looked at varied from 11 to about 20,000. The number of data points varied from 200 to 2 million, okay? So the performance metric here includes accuracy. That's the number of instances when the methodology detects a category correctly. We also looked at the false positives, which is basically, it's basically trying to classify, but it's not true, or false negative is basically there is no error, but it's trying to come up with something completely different. And also we looked at computational time as well. Now, each of these cases, we executed that. We don't want to do just one time. So we executed this 100 instances, and then we averaged them out. These are very typical way of looking at from a statistical perspective, okay? So we call that as a Monte Carlo simulation. So in the application side, we picked about 10-layer network. We picked a tangent hyperbolic because we want to see, we don't have to use a ReLU activation function. We injected some Gaussian noise. We also had some uniform noise. We had about 300 iterations, totally about 100 hidden layer neurons. We split the data about 70% training, 30% testing, And then we pick this B matrix, which is for exploration at random. Okay. So what we found out was we found out consistent classification performance with respect to all data sets. So this is DFA stands for direct feedback alignment. This is one of the methods. FA stands for feedback alignment. SGD, which is very popular method, is called stochastic gradient descent. And EDL is the error-driven learning. And what we noted was the EDL was performing on par with SGD or even better on many of these different methods. Okay, so it's doing a lot better than any of these methods. However, but you can see that there are some data sets like CIFAR 10, CIFAR 100, the image data sets, you see that classification error is only about 65, 70%. So it's still a long way to go compared to some rolling data, bearing data sets, sensorless data sets. You get a much higher accuracy in classification compared to some of the other data sets where you have only like 0.65, 65% and so forth. So it's a 5-layer neural network with tangent hyperbolic activation function. And we executed this 100 runs and results are average. So one of the things I want to tell you was you got to come up with better methods to get better accuracy. And so fewer, smaller networks, we want to train them. And the other problem is we want to cut down the amount of training. Instead of 70%, we want to look at like 40 to 50%, okay? So this is one of the things you got to look at it. And in terms of the generalization performance, you can see the method that I talked about, the EDL, error-driven learning, is called the proposed method. The traditional one is the stochastic gradient descent. And as you can see, as the variance increases from 0 to 1, you see that there is a drop in the performance, the traditional one, whereas the accuracy drop is minimal if it is using the error-driven learning, okay? So basically, what we can conclude is the stochastic gradient descent appears to be unsuitable to train deep networks, whereas the error-driven learning is very successful. So this has been published more recently. It was 2019 is when this was published. Better accuracy with respect to the proposed framework compared to the stochastic gradient descent. So here we want to show the stochastic gradient descent. It has about 7.1% error, whereas the gradient-based updates plus the proposed framework, we can bring it down to 3.8. Whereas if you use the error-driven learning and the neighborhood principle, you can even bring it down to about 1.5% error with just merely using 5-layer neural network with tangent hyperbolic. So we have compared by using the Gaussian noise. You can see that the accuracy is higher than the stochastic gradient descent. Now what we did was we even went ahead and reduced the number of layers, okay? And we went to 3 layers, we went to 10 layers, we also went to 100 layers. So you can see we are comparing different methods. You can see as you increase the number of hidden layers from 3 to 100, you can see that these methods, stochastic gradient descent is 95% accurate, whereas the EDL is 96%. As you increase the number of layers, the accuracy also goes up. And we know that because they get better function approximators, and that's what we are talking about. So we have looked at these, and we are able to kind of realize that whatever we are talking about in the theory, the actual results essentially confirm, and therefore these methods have to be developed. And that's what I was talking about. There's a lot of work going on, a lot of job opportunities, and we call that as a gradient error-driven learning and talked about it. This is being recorded. You can always go back. We also tried it on control theory, not just on classification. So this is basically what we call as a identification problem. So you have a nonlinear plant like a Procter & Gamble, which makes the soap detergent. And so here is the Procter & Gamble soap detergent, and we are trying to control the process to meet certain quality. And here we are using the neural network because this is highly nonlinear. All the soap or the different chemicals you add, there's no model available. So the goal was the neural network has to learn and try to make the quality, the output meet certain requirements, okay? So what we noted was that as with our method, we can actually use shallow networks, which is 3 hidden layers, and we can even reduce the number of iterations. So as you reduce the number of training iterations, you can see 50,000 training iterations, the error is very small. As you reduce the number of training, the error slowly increases, okay? Whereas if you use our method, but then with redo activation function, you can even reduce the error. So with the same number of iterations. So what I'm trying to say is you can actually use some of these in a combination and get the best performance, okay? So the error in prediction is smaller compared to the tangent hyperbolic activation function. We have to use a small learning rate, which is alpha, okay? So with that, I'm going to stop here. I'm going to ask you if you have any questions. So I ended this talk a few minutes early because last session, I didn't see any sort of questions or anybody asking me any questions. So with that, what I'm going to do is I'm going to ask you any questions you may have, okay? Any questions? Again, as I said, don't feel shy. Don't feel shy. It's your ball is in your court. Any questions? Hope you guys understood what we were trying to do. This is one of those cipher data sets. Cipher 1000 has got more number of images here. So any questions? I just don't want you to feel shy. On any of my slides. I try to cut it down a little bit because last time you saw that it took me a little longer. So about 15 minutes or so. This time I thought, okay, I'll open up a little bit more and ask questions. You know, there's a little chat message. Yeah, you can also enter the question as well. If you don't like to answer, you can enter it via chat and I'll be glad to read the message and then answer the question. And don't feel shy. As I said, there's a tremendous number of job opportunities in big data, you know, and machine learning, for instance. And I keep getting every day pretty much an email from companies, over 100 companies, looking for engineers or computer scientists who may be interested to look at these problems. So what I'm saying, they might have applications like insurance, automotive, aerospace, you know, software. There are so many different types of applications I get. So what I'm trying to say is this may be one of the very upcoming area, very hot right now, and machine learning and this, and it's going to be hard the next, I would say maybe in the next decade, okay? And there's also another issue, another problem all of us are looking at it is in the IoT devices, you know, or you know, there's a lot of growth in the IoT, you know, there's quite a bit of proliferation. So we are also looking at how do we bring in the energy part of it, because computationally these are very difficult to process. So the question is, how can we do that in a smartwatch, for instance, you know, or a very low-lying microprocessor, for instance, so, or an embedded system. So there's a lot of work going on in this, you know, how do you crunch data, you know, not as big as like, you know, several terabytes, but or what if you have an IoT device, you got a 1 terabyte, for instance. So there's a lot of opportunity, and I have a lot of videos in AI and stuff, but I'm not going to play them. And if you're not going to ask me any questions, I'm not going to play them. Okay. So one of the things I like is interaction from the students. I know there are at least 22 or 21 or 20 students there. And I can see that you either, if you feel shy, you can enter the question via chat, or, you know, you can always email me. But as I said, last session, this one, I haven't gotten a single email. So any questions? Looks like there is a pin drop silence. So my question is, how many of you really understood? Can you raise your hand using the, Zoom? You know how to raise your hand, right? So you go to more, there's a lot of ways you can do that. Okay. I see there are still students not yet dropped out, but you got to ask questions. So otherwise, I'm assuming that this has gone above your head. No questions. Looks like it's quiet. I see a few people attending. I know Karthik is here, I guess. There are some other ones that I see last time they have attended. So don't feel shy. Let me say this, the simpler question are the ones which are difficult to answer. Any questions here? And I think Dr. Karthik last time mentioned about he's covering those GPUs and stuff, parallel architectures and stuff like that. And so I didn't cover them because sometimes you got to run them on some backend servers, GPUs and stuff. So much of computation. So what I'm trying to say is I didn't even touch upon that side at all. I was only looking at in terms of prediction accuracy and how do we do that? What are the challenges with the big data? And what sort of solutions do exist? Who are interested in this type of data, like healthcare industry and so forth, And so these are some of the things. Okay. So I have talked enough. I think about 50 minutes right now, close to 50. So I expect that at least a few of you can ask me questions. Okay, so there was one, I think it looks like it's coming from faculty. So yeah, one of the questions is if I could say some about the research if some of that have not done. Okay, so let me say this. There are, as I talked about, one of the problems, as I mentioned to you, the most recent one was vanishing gradient. And this was one of the major problems from the academics. Okay. So this is one of the problems. We recently finished it with my PhD student, and we just published these several articles in IEEE or ASCM transactions. Okay, so the vanishing gradient problem is a bigger problem, and we attempted like the heterogeneity and noise and noisy dimensions. Okay, so as I mentioned to you, this is a bigger problem. Where are the applications? We were looking at applications on object recognition and classification. Remember, I showed you those images-based data. We are also looking at for Tesla, for instance, company Tesla, and also Microsoft, for instance. So one of the things Microsoft is interested is healthcare industry. So healthcare industry is a very big industry, tremendous amount of data. Imagine that people like me, for instance, we go and have a checkup every 6 months, and they collect blood samples. They do lots of different types of tests on them. And so there's a lot of dimensions in the data, although the number of data points are less, but there'll be lots of dimensions. So the question is, how do we actually do data analytics? And this is one of the challenges we are looking at. And we're also looking at visual recognition, face recognition. China is doing that quite a bit, okay, for their citizens. Imagine that tremendous number of population in China. So one of the things we are doing is how do we recognize images with minimal data so that it saves energy costs, computational costs, and also it's easier that we can put it on a basically an embedded system. Okay. So some of those that I do as part of my research activity, okay. And as I said, we are looking at some applications like Tesla application, where we are autonomous vehicles, where now cameras are very cheap, very small, and we can use them very easily. In some cases, more than one camera. Surveillance applications, We are also looking at applications in outer space, Mars, greenhouse, the Mars rover projects. So these are some of the projects that I'm currently involved in. Okay. So there are a lot of PhD students who are interested doing this type of research, and we take a very slice of problem. So by the way, if you are interested to do MS or PhD, send me an email. It doesn't have to be me, but there are other faculty members. You just send me an email and say you're interested in this faculty member area. I will just introduce you. Okay. So I don't know whether you are in the 4th years, 3rd years, and so forth. But what I'm trying to say is, if you are getting close to that and you guys are interested to, doing MS or PhD in the US, just send me an email. Okay. Any other questions, guys and ladies? We're about 7 minutes. Any questions? I think somebody got to have some question. We talked about other things as well. And pretty much every software company is involved in this area, like the IBM, even Indian companies, TCS, HCL, for instance, Wipro, quite a few of these. So what I'm saying is, this is not just the problems only facing in the US, but pretty much every nation has this, and every academic guy is working on this problem. The big data challenges, how do we address that? How to make it real time? Humans do that pretty much, right? You turn your head, you see a bunch of objects, and you can recognize it in a fraction of a second. But even the most powerful computers, we still have that problem right now. So I think these are very real practical issues. Okay. Any questions? I know it's not that difficult to ask a question, honestly. Or any questions on the previous session that we covered, where we covered the robotics example, we covered some learning stuff, reinforcement learning. We also talked about the games before we touched upon this big data. And we started from there, right? Where we are trying to recognize these images which are expressed in pixels. And we said there's a tremendous amount of data because you are queuing in so many images and we are feeding through the network. Therefore, we talked about deep learning. Okay. Any questions? I see the slowly dropping off of the attendees. So it's close to 8 o'clock, guys. Couple of minutes left. Okay, so no questions. Shanta, you have any announcements? Or Karthik had some announcements last time. Do you have any announcements? There's a few more minutes at the end, so.
I don't have any announcement, Jag.
Okay,
I think,
so this session will be also recorded and will be posted, right? Just like last
that's
one.
correct. Yeah. Yeah.
My guess is so. All right, so Shanta, I don't think I had any questions even last time. So I don't know. What do you think? We should just cut it. It's only 5 more minutes left. So
Right. I think asking questions is part of learning. So the students need to develop that habit of asking questions. If you don't ask questions, you don't really expand your mind. So I encourage the students to ask questions, and there are a couple of ways to do that. You can either raise your hand and do it verbally, or you can post the question on the chat. For the next time, keep in mind that the more you interact, the more you learn. So Jag has given you some really very interesting things to think about, and I'm sure you have questions. Even if you don't ask it now, perhaps you can ask it later. And I'm sure you're all interested in what's going on in the world. And as Jag pointed out, this is one of the hottest areas when you go for a job. So the more you learn about big data and all the implications of AI and so on, the better you are with your career opportunities. That's it for me, Jack.
Yeah, thank you. I think that's nice of you. So I don't have anything. It looks like they're very quiet and we are getting close to about 8 o'clock. So
Yep.
can I end the session? Is it okay?
Yeah, please.
All right. Thank you, Shanta. Nice meeting you. Okay. Face to face.
Thank you, Jack, for your dedication to CEG and giving it back in terms of paying forward.
Let's hope
So
it.
thank you.
Yeah, I hope, like as you said, hope these students will benefit and hope that they will be in touch with us. At least if they feel shy, they can always email us, right? So,
Yeah, absolutely. Yeah.
all right. Thank you, guys, and have a good night. Okay. Bye.
Bye.